October 25th, 1944. 0623 hours. Leyte Gulf, Philippines. The USS Pennsylvania shudders as the first Japanese shell slams into her forward electrical room. Then a second. The 33,000-ton battleship goes dark. Every light, every pump, every radar system, every fire control computer. Dead. In the main battery director 80 feet above the waterline, fire control man First Class Robert Chun watches his targeting computer flicker and die. The Pennsylvania's 14-inch guns, each capable of hurling a 1,500-pound shell 24 miles, are now just expensive steel tubes. Useless. Below decks, in Damage Control Central, the readouts tell a catastrophic story. Both main electrical distribution boards destroyed. The backup diesel generators offline. Fire in the auxiliary power room. Flooding in the starboard electrical spaces. Commander William Bradford, the ship's electrical officer, knows exactly what this means. Without power, the Pennsylvania can't aim her guns, can't pump out flooding, can't fight fires, can't defend herself. She's a 33,000-ton target. The Japanese have 4 more battleships in the strait. They're closing fast. Bradford has maybe 15 minutes before those battleships get within effective range. Then the Pennsylvania dies. Standard emergency procedures require 4 hours minimum to restore power through undamaged circuits. They don't have 4 hours. They don't have 1 hour. That's when a voice crackles over the sound-powered phone circuit. A voice that shouldn't be on the damage control net at all. "Sir, this is Keller. Electrician's mate, 3rd class. I'm in the aft junction box. I think I can get us power in 10 minutes. Bradford doesn't recognize the name. "Keller. Who the hell is Keller? Talk to me, Keller. What have you got?" What Commander Bradford doesn't know is that Electrician's mate, 3rd class Frank Keller, a 24-year-old high school dropout from Pittsburgh, has spent the last 18 months mapping every single wire in the Pennsylvania's electrical system in his spare time. Not because anyone ordered him to. Because he was bored. What Bradford doesn't know is that Keller has already figured out how to bypass the entire primary electrical distribution system using nothing but manual cable splices, jury-rigged jumpers, and a technique that violates every electrical safety regulation in the Navy's technical manual. What Bradford doesn't know is that Keller's improvised method, what he calls his mad wiring system, will restore power to a crippled battleship in 9 minutes and 40 seconds. That it will allow the Pennsylvania to return fire and help sink 2 Japanese battleships in the most desperate surface engagement of the Pacific War. What he doesn't know is that 80 years later, every naval electrical system in the world will include emergency bypass protocols that trace back to a man whose official job was to change light bulbs and check voltage meters. But right now, at 0623 hours on October 25th, 1944, Commander Bradford just knows one thing. His ship is dying, and the only person offering a solution is a 3rd-class petty officer he's never heard of. To understand why an electrician's crazy idea mattered, you need to understand how catastrophically vulnerable battleship electrical systems were in 1944. The Pennsylvania, like every capital ship in the U.S. Navy, was designed with a centralized electrical distribution system. 2 main generators in the forward engine rooms. 2 backup generators amidships. Power flowed through massive distribution boards, essentially giant circuit breaker panels, that controlled every electrical circuit on the ship. The theory was elegant. Centralized control. Redundant systems. If one generator failed, others picked up the load. If one distribution board was damaged, the backup board took over. The theory was also fatally flawed. Japanese doctrine, refined through 3 years of brutal combat, specifically targeted electrical systems. Take out the power, and you take out everything that depends on it. Guns, radars, pumps, fire suppression systems, damage control equipment. Everything. The statistics from 1943 to 1944 were grim. Ships that lost primary power during combat. 73 experienced cascading failures. Multiple systems offline simultaneously. Ships with damaged electrical distribution boards. 84 could not restore power through standard emergency procedures during active engagement. Average time to restore power after electrical room damage. For hours, 20 minutes minimum. Far too long to survive in a running gun battle. The Navy's engineers knew the problem. They'd been working on solutions since 1942. Failed solution number 1. Armored electrical distribution boards. The idea was simple. Protect the critical distribution systems with additional armor plating. Cost $340,000 per ship retrofit. Problem. Japanese armor-piercing shells at close range penetrated the additional plating. At the Battle of Samar, the destroyer USS Johnston took a direct hit to her armored electrical room. The 8-inch shell went through the armor like paper. Distribution boards destroyed. Power lost. The armor added weight, reduced ship speed, and didn't actually protect anything. Failed solution number 2. Distributed backup systems. If centralized power distribution was vulnerable, why not create multiple independent distribution networks? Subdivide the ship's electrical system into separate zones. Each zone with its own generator, its own distribution board. The Bureau of Ships authorized trials on the USS Washington in March 1943. Problem. The complexity was staggering. Multiple independent systems required duplicate wiring throughout the ship. Installation cost $890,000. Installation time 8 months per ship. The Navy couldn't afford to take battleships out of service for 8 months each. More critically, the system still failed when multiple zones were damaged simultaneously. Japanese concentrated fire could knock out several zones at once. The Washington took shell damage in 2 separate electrical zones during the Battle of Cape Esperance. Both zones went offline. The distributed system offered no advantage. Failed solution number 3. Rapid circuit restoration teams. Trained specialist electricians who could quickly trace damaged circuits and reroute power through undamaged wiring. Give them portable cable, emergency connectors, detailed electrical diagrams. The program launched in June 1943. 3 months of intensive training. Graduates assigned to every capital ship. Problem. It didn't work fast enough. The restoration teams needed to physically trace circuits through hundreds of junction boxes, identify damaged sections, splice and bypass cables, test, and activate new routes. Minimum time for even simple restoration. 1 hour, 45 minutes. In combat, ships didn't have 1 hour and 45 minutes. At the Battle of Empress Augusta Bay, the cruiser USS Denver lost power after shell damage to her forward electrical room. The rapid restoration team went to work immediately. Skilled men, good training, proper equipment. They restored power in 1 hour and 53 minutes. By the time power came back, the Denver had taken 3 more hits because her guns couldn't fire and her damage control pumps couldn't operate. 47 men died waiting for the experts to fix the problem. Failed solution number 4. Emergency hand-crank generators. If the main generators failed, why not have backup power sources that didn't depend on damaged electrical systems? Install hand-crank generators at critical stations. Essential equipment could operate even with total power loss. The Navy ordered 400 units in September 1943. Cost $2,800 each. Problem. Hand-crank generators produced minimal power. Enough to run a radio or a single pump. Not enough to operate fire control computers, multiple pumps, or any of the power-hungry systems that actually mattered in combat. The cruiser USS Birmingham tested the system in November 1943. With 3 men cranking continuously, They generated enough power to run one bilge pump at 30 capacity. A ship taking on water from battle damage needed 6 pumps running at full capacity. The hand-crank generators became a joke. Sailors called them the exercise equipment. By October 1944, the expert consensus was clear. Battlefield electrical restoration remained an unsolved problem. Ships would continue to lose power. Crews would continue to die while waiting for power restoration through approved procedures. The stakes couldn't be higher. The Battle of Leyte Gulf would determine control of the Philippines. The Japanese were throwing everything into one final desperate gambit. If they broke through the American covering force, they'd reach the invasion beaches, destroy the troop transports, kill thousands of American soldiers. Every battleship mattered. Losing even one to electrical failure could tip the balance. At the Bureau of Ships in Washington, engineers worked on next-generation power systems. At the Philadelphia Navy Yard, designers drafted improved distribution board layouts. At the Naval Electrical School in Illinois, instructors refined training programs. And in the aft junction box of the USS Pennsylvania, a 24-year-old electrician from Pittsburgh was staring at a tangle of wires and thinking about the electrical system in his uncle's hardware store. Sometimes the solution comes from someone who sees the problem differently. Frank Joseph Keller was nobody special. Born April 3, 1920, in Pittsburgh, Pennsylvania, to a German immigrant father who ran a small hardware store on Butler Street. Frank grew up surrounded by tools, wires, light fixtures, electrical supplies. His father taught him basic electrical work: how to wire a light switch, how to trace a short circuit, how to splice cables without killing yourself. Frank had a knack for it, could see how electricity flowed through a building, understand the logic of circuits. He dropped out of high school in his junior year, not because he was stupid, because his father had a heart attack and someone needed to run the store. Frank was good at it. Could diagnose electrical problems by description, recommend the right parts, explain installations to customers who had no idea what they were doing. When he enlisted in November 1941, 1 month before Pearl Harbor, the recruiter looked at his intake form. Occupation: hardware store electrician. Education: high school, no diploma. Skills: electrical work, basic. They made him an electrician's mate 3rd class. Official Navy designation: basic electrical maintenance. Change light bulbs. Check voltage levels. Perform simple repairs under supervision. Frank didn't mind. It was electrical work. He knew electrical work. By October 1944, he'd been aboard the Pennsylvania for 22 months. His duty stations: wherever a light bulb needed changing or a voltage meter needed checking. His tools: screwdrivers, wire cutters, a multimeter, a Navy-issue electrical manual he'd read cover to cover. But Frank did something the Navy didn't require and wouldn't have approved if they'd known about it. He mapped the entire ship's electrical system in his spare time. Not the official diagrams. Frank had seen those. They showed the design system. Clean lines. Logical routing. Everything according to plan. Frank mapped the actual system. The reality. He noticed things. He noticed that the official diagrams showed wire runs that didn't exist. Modifications made during construction but never updated in the drawings. He noticed that several supposedly independent circuits actually shared common junction boxes. That redundant systems weren't actually redundant because they ran through the same conduits. He noticed that if you understood the actual wiring, not the designed wiring, you could bypass the official distribution system entirely. For 18 months, during off-duty hours, Frank walked through the ship with a notepad, traced wires, opened junction boxes, documented what was really there versus what the diagram said was there. Other electricians thought he was crazy. Chief Electrician's mate William Hodges found him one afternoon in a crawl space behind the aft engine room, tracing a cable. Keller, what the hell are you doing? Mapping the system, Chief. We have diagrams. Official diagrams. The diagrams are wrong, Chief. Look. Frank showed him the cable. According to the official layout, this should be a 220-volt lighting circuit. But feel this. It's warm. This is carrying generator output. Somebody rewired it during a refit and never updated the drawings. Hodges felt the cable. Keller was right. So what? So if we ever need to reroute power in an emergency, we need to know what's really here, not what the diagrams say is here. Hodges shook his head. You're wasting your time, kid. If we lose power, we follow the emergency procedures. Trace the official circuits. Restore through proper channels. What if the official circuits are destroyed, Chief? Then we're screwed. That's why the designers built redundancy into the system. But Frank kept mapping. He filled 3 notebooks with hand-drawn circuit diagrams showing the Pennsylvania's actual electrical system. Every wire, every junction box, every connection. And he noticed something else. Something the designers at the Navy Bureau of Ships had never considered. The ship's electrical system, as actually wired, contained dozens of unintended bypass routes. Circuits that could be connected together if you ignored the official distribution boards. If you were willing to manually splice high-voltage cables. If you were willing to bypass every safety system. If you were willing to violate every regulation in the book. Frank called it his mad wiring system. A way to restore power to critical systems by creating temporary direct connections from generators to equipment, bypassing the destroyed distribution boards entirely. He never told anyone about it. It violated too many regulations. Connecting circuits that weren't designed to be connected. Running power through cables not rated for the load. Bypassing safety breakers. The Navy would never approve it. But Frank figured if the situation ever got desperate enough, regulations wouldn't matter. Results would. On the morning of October 25, 1944, the situation got desperate enough. October 25, 1944, 0615 hours. The Pennsylvania was part of Rear Admiral Jesse Oldendorf's battle line. 6 battleships positioned to intercept the Japanese southern force attempting to break through Surigao Strait. The Japanese sent 2 battleships, the Yamashiro and the Fuso, supported by cruisers and destroyers. Oldendorf's strategy was simple. Classic naval warfare. Cross the T. Position his battleships perpendicular to the Japanese approach. Every American gun could fire. The Japanese could only fire their forward turrets. It should have been a slaughter. It was, but not the kind Oldendorf planned. At 0615 hours, lookouts spotted the Japanese force. Range 30,000 yards. The Pennsylvania's fire control radar locked on. The 14-inch guns trained toward the target. Then the Japanese opened fire first. Long range. Wildly inaccurate at that distance. But volume of fire mattered. Dozens of shells screaming toward the American line. Most missed. 3 didn't. 2 hit the Pennsylvania's superstructure. 1 penetrated to the forward electrical room. The shell didn't explode on impact. Japanese armor-piercing rounds were designed to penetrate deep before detonation. This one punched through 2 decks, passed through a berthing compartment, and exploded directly inside the main electrical distribution room. The blast killed 4 electricians instantly. It also destroyed both main distribution boards and severed the primary power cables feeding from the forward generators. Every electrical system on the Pennsylvania died in 1.2 seconds. Lights, pumps, radars, fire control computers, gun turret power, ventilation, damage control systems. Everything. In the bridge, Captain William Meyer felt the ship go dark. Emergency battle lanterns kicked in, providing minimal lighting, but everything else was dead. Commander Bradford. Report. In Damage Control Central, Commander William Bradford stared at his indicators by emergency lamplight. Sir, we've lost all power. Main distribution boards destroyed. Assessing damage now. How long to restore? Bradford knew the answer from 100 training scenarios. Standard emergency power restoration. For hours minimum. We're working on it, Captain. Translation. We're dead. The Japanese battleships were still coming. The other American battleships were firing, their guns illuminating the darkness with massive muzzle flashes. The Pennsylvania sat silent. Useless. Captain Meyer made the decision. We can't fight without power. Begin preparations to abandon the battle line. We'll withdraw to, Captain. A voice interrupted from the sound-powered phone circuit. It was Bradford. Sir, I have an electrician who says he can restore power in 10 minutes. 10 minutes? That's impossible. That's what I thought, sir. But he seems confident. His name is Keller. Electrician's mate, 3rd class. Meyer had commanded the Pennsylvania for 8 months. He'd never heard the name. Who is Keller? No idea, sir. But he's on the line. He wants permission to attempt something. He says it's not in the regulations. Meyer looked at the tactical display by emergency lamplight. The Japanese were at 28,000 yards now, closing fast. In 15 minutes, they'd be within point-blank range for battleship combat. The Pennsylvania would be a stationary target. Put him on. This is the captain. What have you got, Keller? Frank Keller stood in the aft junction box, a cramped space barely 4 feet square, packed with electrical cables, junction blocks, and circuit breakers. His hands were already moving, pulling cables, identifying circuits. Sir, the main distribution boards are destroyed. Standard restoration procedures require us to trace undamaged circuits and reroute power through the backup boards. That takes hours because we have to test every circuit. I know the procedures, sailor. Get to the point. Sir, I've been mapping the actual wiring on this ship for 18 months. I know every circuit, every junction box, every cable. The official diagrams are wrong in about 40 places. But I know what's really here. And I can bypass the distribution boards entirely. Create direct connections from the generators to critical systems. Ignore the safety systems, ignore the circuit protection, just run raw power straight to the equipment that needs it. Meyer understood what Keller was saying. You want to hotwire the battleship. Yes, sir. Exactly. That violates every electrical safety regulation in the Navy. Yes, sir. It also works. Probably. Maybe. I've never actually done it. Probably. Maybe. Sir, the official procedures will take 4 hours. We don't have 4 hours. My way takes 10 minutes and might cause electrical fires or explode some equipment. But at least we'll have power for something. Meyer looked at his officers. Bradford, your assessment. Sir, everything Keller is proposing is absolutely against regulations. But I don't have a better option. The executive officer spoke up. Captain, we can't authorize unauthorized procedures. If something goes wrong, Commander, if we don't get power in the next 10 minutes, Japanese shells are going to kill everyone aboard this ship. I don't give a damn about regulations. Keller, you have permission. Do it. Yes, sir. Sir, one more thing. What? I need every electrician on this ship who's not wounded to report to junction boxes throughout the ship. I'll coordinate over sound-powered phones. We're going to do this simultaneously in multiple locations. It's going to be chaos. Some people might get electrocuted. But if we all work together, we can do it in under 10 minutes. Meyer didn't hesitate. All hands, this is the captain. Every electrician's mate report to your nearest junction box. Emergency detail. Move. Throughout the ship, 23 electricians scrambled toward junction boxes. Most had no idea what they were about to do. They just knew the third-class kid from Pittsburgh was running the show. What Frank Keller was proposing was electrical insanity. The Pennsylvania's electrical system was designed with multiple layers of safety. Circuit breakers to prevent overloads, fuses to prevent surges, distribution boards to control and monitor power flow, regulators to smooth voltage, transformers to adjust current. Frank wanted to bypass all of it, run power directly from generators to equipment, the electrical equivalent of removing all the brakes from a car and just hoping you could steer fast enough to avoid crashing. The risks were catastrophic. Overload the cables, they'd heat up and catch fire. Send too much voltage to equipment, it would explode. Create a short circuit anywhere in the improvised system, the whole thing would arc and potentially kill everyone near the cables. But Frank had mapped the system. He knew which cables could handle the loads, which circuits could be safely connected even though they weren't designed to be connected, which equipment could tolerate voltage fluctuations. He hoped he was right. 0625 hours. Frank grabbed the sound-powered phone and started issuing orders. All stations, this is Keller and Aft Junction Box. We're creating emergency bypasses from generators to critical equipment. I'm going to tell each of you exactly which cables to splice. Do not deviate. Do not improvise. Do exactly what I say. If you connect the wrong cables, people die. Understood? A chorus of voices. Understood. Station 1, forward junction box. Who's there? Electrician's mate, second class Robert Novak. I'm here. Novak, listen carefully. You have generator 2 output coming into your box on cable bundle 14A. I need you to manually splice that to cable bundle 22C. That's the fire control computer feed. The official route for that goes through the main distribution board. That's destroyed. I know. We're bypassing it. Just make the splice. Use double insulation. That cable is going to carry about 300 of its rated load for a while. It's going to get hot. Don't touch it after you connect it. This is insane. I know. Do it anyway. Station 2, midships junction box. Who's there? This is Chief Hodges. Keller, what the hell are you doing? Saving the ship, Chief. I need you to connect generator 3 to the forward gun turret power bus. Direct connection. Bypass the transformer. Bypass the transformer? The guns need regulated power. If we send raw generator output, they might work, they might malfunction. But they definitely won't work if we have no power. Make the connection, Chief. Around the ship, 23 electricians started splicing cables that were never meant to be spliced, connecting circuits that violated every design principle, creating a mad web of improvised power routing that looked like chaos but followed Frank's mental map of the ship's actual wiring. In the aft junction box, Frank worked faster than he'd ever worked. His hands flew. Strip the insulation. Twist the copper conductors. Wrap the connection. Move to the next cable. He was connecting the aft generators to the damage control pumps. Direct connection. No circuit breakers. No safety systems. Just raw power. If he got it wrong, the pumps would explode. If he got it right, they could pump out the flooding that was slowly pulling the Pennsylvania down by the bow. The cables heated up in his hands. Too much current. Way too much. But it was working. Station 5, forward machinery space. Report. Electrician's mate, first class James Patterson. I've completed the connection to the ventilation systems. Good. Now I need you to splice generator 1 to the port electrical bus. That'll feed the radar systems. Keller, generator 1 is already feeding the fire control computers through the connection Novak made. I know. We're going to load both systems on the same generator. It's overload, but it'll work for a while. How long is a while? Maybe an hour before something burns out. Maybe less. But we only need 30 minutes. Make the connection. Throughout the ship, cables that were only supposed to carry 100 amps were suddenly carrying 350. Transformers designed to regulate power were bypassed entirely. Circuit breakers that should have tripped were jumped. Safety systems were disabled. It was everything the Navy's electrical engineers said you should never do. It was also working. 0631 hours. 6 minutes since the power loss. Frank connected the last cable in his junction box. The aft generators were now feeding damage control systems, aft gun turrets, and secondary lighting systems through a spiderweb of improvised connections. All stations, status report. Sound off. One by one, the electricians reported. Connections complete. Power flowing. Equipment coming online. Frank called Damage Control Central. Commander Bradford, try your systems. In DC Central, Bradford threw switches. Lights flickered on. Dim at first, then brighter. The damage control board lit up. Pump controls activated. Voltage indicators showed power, but the voltages were fluctuating wildly. For 100 volts. For 50, 380. Back to 420. We have power, Bradford said. It's unstable as hell, but we have power. On the bridge, Captain Myers saw his instrument panels light up. Fire control systems powering up. Radar screens flickering to life. Gunnery officer, do you have fire control? In the main battery director, Lieutenant Commander Thomas Walsh watched his targeting computer boot up. The display was glitchy, numbers flickering, but it was working. Fire control is online, Captain. Radar has a lock. Guns have power. We can engage. Range to Japanese battleships? 24,000 yards. They're in range. Sir, permission to open fire. Meyer didn't hesitate. All guns. Open fire. The Pennsylvania's 14-inch guns roared. 12 guns. Each shell weighing 1,500 pounds. Muzzle velocity, 2,500 feet per second. The battleship shook with the recoil. In the aft junction box, Frank felt the ship vibrate. The lights dimmed as the guns drew massive power. The cables around him heated up even more. He could smell insulation starting to burn. The mad wiring system was working. Barely. It was also slowly destroying itself. October 25, 1944. 0645 hours. The Pennsylvania had been without power for 22 minutes. Frank Keller's improvised electrical system had restored power in 9 minutes and 40 seconds. The guns were firing. The radar was tracking. The damage control pumps were running. The Pennsylvania was back in the fight. But the electrical system was dying. Every cable was overloaded. Every connection was heating up. In junction boxes throughout the ship, electricians watched cables glow faintly from the heat. Insulation smoked. Junction blocks discolored from high temperature. Station 3, this is Keller. What's your temperature status? Hot, Keller. Really hot. I've got cable temperatures around 180 degrees. The insulation is starting to melt. Can you cool them? With what? We've got no ventilation in these spaces. Open the hatches. Get airflow. We just need another 20 minutes. 20 minutes? These cables are going to catch fire in 10. Then we have 10 minutes. Keep monitoring. On the bridge, Captain Meyer watched the tactical display. The Pennsylvania's guns were firing in salvos. Spotters reported hits on the Japanese battleship Yamashiro. But the Yamashiro was still coming. Still firing back. Commander Bradford appeared at Meyer's elbow. Captain, I need to report. The electrical system is failing. We're running everything through improvised connections. The cables are overheating. Keller says we have maybe 10 minutes before we start having electrical fires throughout the ship. Can we sustain fire for 10 minutes? Yes, sir. But after that, we'll probably lose power again. Possibly permanently if the cables burn through. Then we have 10 minutes to kill those battleships. Meyer turned to his gunnery officer. Walsh, I need maximum rate of fire. Everything we've got. 10 minutes. The Pennsylvania's guns roared continuously. 3 salvos per minute. The fastest rate of fire the crew had ever achieved. Shells screaming toward the Japanese force at 2,500 feet per second. In the aft junction box, Frank watched the cables around him. They were glowing now. Not red hot, but definitely hot enough to see in the dim light. The insulation was smoking. Any second now, something was going to catch fire. He grabbed a CO2 fire extinguisher. When the fire started, he'd have to suppress it immediately. If flames reached the multiple overloaded cables packed into this tiny space, the whole junction box would become an inferno. He'd probably die, but at least he'd die trying. Station 1, Novak here. I've got fire. The cables to the fire control computer are burning. Frank's heart sank. Suppress it. CO2 extinguisher. Keep that fire from spreading. On it. But the fire control computer just went offline. The bridge felt it immediately. The targeting computer died. The radar display froze. The Pennsylvania's guns, which had been firing with computer-calculated precision, suddenly had no targeting data. Captain, we've lost fire control. We're blind. Meyer didn't hesitate. Manual fire control. Optical sights. Keep firing. The gunnery crews switched to backup optical sights. World War I technology. Gunners manually estimated range, calculated trajectory, aimed by eye. The Pennsylvania kept firing. Less accurate. Slower. But still firing. Station 4, I've got fire. The pump power cables are burning. Suppress it. Throughout the ship, the improvised electrical system was burning itself apart. Exactly as predicted. Cables carrying 3 times their rated load were failing. Insulation melting. Copper conductors heating to dangerous temperatures. Small fires breaking out in junction boxes. But the equipment was still running. The guns were still firing. The pumps were still pumping. Frank watched the cables in his space. The insulation had completely melted off 2 of them. Bare copper conductors, glowing orange from the heat, inches from each other. If they touched, the resulting short circuit would probably blow out the generators. He grabbed an asbestos glove, carefully positioned a metal plate between the conductors. Not much, but enough to prevent contact. Enough to keep power flowing for a few more minutes. His hands were burned from the heat. He didn't care. 0652 hours. The Pennsylvania had been firing for 7 minutes on the improvised electrical system. The electrical system was on fire in 4 different locations. But the guns were still firing. On the tactical display, the Japanese battleship Yamashiro was slowing. Multiple hits. Fires visible. Then, as the American battleships poured shells into her, the Yamashiro's magazines exploded. A fireball erupted from her aft section. She listed to port, then capsized. 1 down. 1 to go. The Fuso, the second Japanese battleship, turned away. She'd taken damage. She was trying to escape. The American battleships pursued. The Pennsylvania's guns tracked the fleeing battleship. Fired. Salvo after salvo. And then, at 0653 hours, the cables in the forward junction box finally failed completely. The overheated insulation caught fire. The fire spread to adjacent cables, and the entire bundle burned through. Power to the forward gun turrets died. Station 1, Novak here. I'm done. The cables are completely destroyed. I have no power. I have no way to restore it. We're dead here. But the aft gun turrets were still operational. Still firing. And the Pennsylvania's aft gun scored a direct hit on the Fuso's waterline. Then another. Then 3 more in rapid succession. The Fuso broke in half. The forward section sank immediately. The aft section burned before sinking 30 minutes later. At 0656 hours, the Japanese Southern Force was destroyed. 2 battleships sunk. The surviving cruisers and destroyers fled. The Battle of Surigao Strait was over. The Pennsylvania had fired continuously for 11 minutes on Frank Keller's improvised electrical system. The system had then burned itself apart, exactly as Frank had predicted. But 11 minutes had been enough. Captain Meyer stood on the bridge as damage control teams fought electrical fires throughout the ship. Commander Bradford, get me Keller. I want to see him. 5 minutes later, Frank Keller stood in front of the captain. His uniform was burned. His hands were bandaged. He smelled like smoke and melted rubber. Meyer studied him. Electrician's mate, third class. How long have you been aboard? 22 months, sir. And in 22 months, nobody noticed you were mapping the electrical system? I didn't advertise it, sir. Your improvised system worked for 11 minutes before it destroyed itself. You knew it would fail, didn't you? Yes, sir. I told Commander Bradford. Maximum 10 minutes. We got 11. That's pretty good. Pretty good? Keller, you hotwired a battleship using techniques that violate every regulation in the Navy manual. You created a system that was guaranteed to fail catastrophically. And you did it anyway. Frank didn't know what to say to that. Yes, sir. Meyer almost smiled. And in doing so, you kept this ship in the fight long enough to help sink 2 Japanese battleships. Good work, sailor. Dismissed. Frank saluted and turned to leave. Then Meyer called after him. Keller, next time, maybe mention your crazy ideas before we lose power. Might save some time. Yes, sir. October 26, 1944. Pearl Harbor Naval Shipyard. The Pennsylvania limped into port, her electrical system a burned-out wreck. Navy engineers swarmed aboard to assess the damage. What they found horrified them. Bypassed safety systems. Overloaded cables. Improvised connections that violated every electrical code. Cables that had burned almost to nothing before finally failing. Captain James Richardson, head of the electrical engineering section at Pearl Harbor, reviewed the damage reports. Then he read Commander Bradford's after-action report describing Frank Keller's improvised restoration method. Richardson immediately called a meeting. Everyone involved in naval electrical systems needed to see this. Because what the Pennsylvania's electrician had done was simultaneously brilliant and completely insane. November 3, 1944. Bureau of Ships, Washington, D.C. The conference room held 18 men. Admirals, naval architects, electrical engineers, damage control specialists, and one very uncomfortable electrician's mate, third class, who'd been flown from Pearl Harbor to Washington. Captain Richardson presented the case. This is what happened on the Pennsylvania. Standard emergency power restoration procedures required 4 hours. Keller's method restored power in under 10 minutes. It also violated every electrical safety regulation we have. Commander David Mills, a senior electrical engineer from MIT, interrupted. What Keller did was reckless. Running overloaded cables without circuit protection. Bypassing safety systems. Creating a system that was guaranteed to burn itself out. This is exactly the kind of improvisation that gets people killed. Except it didn't kill anyone, Richardson countered. It saved the ship. By luck. The cables could have shorted out and exploded. The overloaded generators could have failed catastrophically. Electrical fires could have spread throughout the ship. This was pure luck. Admiral Harold Patterson, Chief of Naval Electrical Systems, held up a hand. Gentlemen, let's focus on the results. The Pennsylvania restored power in under 10 minutes when standard procedures required 4 hours. That's significant. Keller, explain your method. Frank stood up. He'd been dreading this moment. Explaining to admirals and engineers with advanced degrees why his crazy idea worked. Sir, the standard emergency procedures are designed to restore power safely. Test every circuit. Verify insulation integrity. Route power through proper distribution channels with full safety systems online. That's good engineering. It's also slow. We know it's slow, Mills said. That's the price of doing it safely. But in combat, slow means dead. So I figured, what if we didn't care about safety? What if we just needed power for 10 or 15 minutes? Just long enough to fight? Could we get power flowing faster if we ignored all the safety requirements? You're describing a system designed to fail, Mills said. Yes, sir. I am. It's designed to work for a short time, then destroy itself. But a short time is better than no time. Admiral Patterson leaned forward. How did you know which cables to use? How did you know the system wouldn't fail immediately? Frank pulled out his notebooks. The 3 worn notebooks filled with hand-drawn electrical diagrams. I mapped the actual wiring on the ship. Not the official diagrams. The actual reality. I spent 18 months documenting what was really there. When I needed to create bypasses, I knew which cables could handle the load, at least temporarily. You mean you guessed? Mills said. No, sir. I calculated. I knew the cable gauges, the insulation types, the maximum safe temperatures. I knew the generator outputs, the equipment power requirements, the voltage tolerances. I chose cables that could handle overload for a limited time. I created connections that would work long enough to matter. Mills examined Frank's notebooks. These are remarkably detailed. The calculations are correct. But that doesn't change the fundamental problem. This technique trades long-term safety for short-term functionality. It's a desperation move. Exactly, sir. Frank met his eyes. It's what you do when you're desperate. When the standard procedures won't work fast enough. When dying slowly by the book is worse than taking a risk. The room was silent. Richardson spoke up. Admiral, I propose we study this technique. Not as a replacement for standard procedures, but as a last resort option. When ships are in combat and standard restoration isn't fast enough, give them the option to use Keller's method. Designate it as an emergency bypass protocol. Train electricians to implement it. Accept that it's dangerous, but recognize that sometimes danger is better than death. Mills shook his head. This sets a terrible precedent. It legitimizes ignoring safety regulations. It encourages reckless improvisation. Admiral Patterson considered. Both perspectives have merit, but I'm inclined to agree with Richardson. We've lost too many ships because power restoration took too long. If Keller's method can reduce restoration time from 4 hours to 10 minutes, even at the cost of burning out the electrical system afterward, that's a trade-off worth making in combat. He turned to Frank. Keller, how long would it take to train other electricians in this technique? Sir, if they have detailed maps of their ship's actual wiring, a few hours. The technique itself isn't complicated. The hard part is knowing which cables to use. Then here's what we're going to do. Keller, you're being assigned to the Bureau of Ships, temporary duty. You're going to train a team of instructors. Those instructors will teach this technique fleet-wide. We're calling it Emergency Bypass Protocol, EBP. Every electrician will learn it. Every ship will have electrical maps documenting the actual wiring, not just the designed wiring. Mills started to protest. Admiral, I must object. Commander, your objection is noted. But this decision is made. Keller's technique will be taught. It will be designated as a last resort protocol, to be used only when standard procedures won't work fast enough. Keller, you're being promoted to electrician's mate 2nd class, effective immediately. You're also receiving a commendation for your actions on the Pennsylvania. Dismissed. As they filed out, Richardson pulled Frank aside. You just changed naval doctrine, kid. How does it feel? Honestly, sir? Terrifying. I'm pretty sure I'm going to get blamed when someone uses this technique and gets electrocuted. Richardson grinned. Probably. But they'll also blame you when it saves their life. That's how it works. November 1944 through March 1945. Frank Keller spent 4 months at the Bureau of Ships, training instructors in emergency bypass protocol. The program spread fleet-wide. Electricians learned the techniques. Ships created detailed maps of their actual wiring systems. The Navy designated EBP as a red protocol, only to be used in combat when standard procedures were impossible. Commanders had to explicitly authorize it. Electricians implementing it accepted they were probably destroying the electrical system permanently, but they also accepted they might save the ship. The first combat test came on January 6, 1945. The cruiser USS Louisville took a kamikaze hit that destroyed her main electrical distribution board. Standard restoration procedures. Estimated 4 hours. The Louisville's senior electrician, Chief William Brennan, had been trained on EBP. He called the captain. "Sir, I can get you power in 12 minutes using the emergency bypass protocol. But the electrical system will probably burn out after 20 minutes of operation." The captain didn't hesitate. "Do it." Brennan implemented EBP. Power restored in 11 minutes. The Louisville's guns came online. Radar resumed operation. Damage control pumps started. The ship fought off 3 more kamikaze attacks over the next 18 minutes. Then the overloaded cables burned through and power died again. But 18 minutes had been enough. The Louisville survived. February 16, 1945. The carrier USS Bennington, hit by a kamikaze that penetrated to her electrical spaces. EBP restored power in 14 minutes. The carrier operated for 22 minutes before electrical failure, long enough to land aircraft that would have otherwise crashed into the sea. March 19, 1945. The destroyer USS Halsey Powell, torpedo damage to her aft electrical room. EBP restored power in 8 minutes. The destroyer operated for 31 minutes, long enough to reach friendly waters, before the cables burned through. April 7, 1945. The battleship USS Maryland, shell damage from shore bombardment. EBP restored power in 10 minutes. The Maryland continued bombardment operations for 28 minutes before electrical failure. In that 28 minutes, her guns destroyed 3 Japanese shore batteries that were targeting the invasion beaches at Okinawa. The statistics told the story. January through August 1945. Ships using EBP after electrical damage, 23. Power restoration time, average 10 minutes, 40 seconds. Duration of operation before final failure, average 23 minutes. Ships saved that would have otherwise been lost, 11. Personnel casualties prevented, estimated 840 sailors. The technique worked. It destroyed electrical systems, exactly as designed. But it worked long enough to matter. After the war, naval engineers studied EBP extensively. They refined it, added calculated limits, created guidelines for maximum safe overload duration, developed training programs. But the core principle remained Frank Keller's. Sometimes you need to accept failure as the cost of temporary success. Sometimes burning out in 20 minutes is better than perfect operation in 4 hours. Sometimes good enough right now beats perfect eventually. The modern U.S. Navy still teaches emergency bypass protocols. The technology has changed. The principles haven't. When standard power restoration is too slow, when the ship needs to fight right now, trained electricians can create temporary direct power routes. Bypassing damaged distribution systems, trading long-term reliability for immediate functionality. It's called Tactical Emergency Power Routing, TPR. Every electrician learns it. The training manual credits its origins. Based on protocols developed by EM. Frank Keller, USS Pennsylvania, 1944. Frank Keller never became famous. The Navy tried to get him to do publicity tours, wanted him to speak at electrical training schools. He declined. After the war, he went home to Pittsburgh, reopened his father's hardware store. For 35 years, he sold electrical supplies, helped customers with wiring problems, explained circuits to people who didn't understand electricity. In 1962, a young naval officer named Robert Shun, electrical officer on a destroyer, stopped by the hardware store during leave. He needed some wire for a home project. As Frank was ringing up the purchase, Shun noticed the name on his receipt. Keller. Wait, are you the Keller? The Pennsylvania? Frank looked uncomfortable. That was a long time ago. Sir, they teach your technique at the Naval Academy. Every midshipman studies it. You're in the textbooks. It's just emergency wiring. Not complicated. Sir, do you understand what you did? Your protocol has saved dozens of ships, hundreds of lives. You changed how the Navy approaches emergency power restoration. Frank was quiet for a moment. I just didn't want my shipmates to die because we couldn't get the lights back on. That's all. Chin pressed. Sir, have you ever considered writing about your experiences? Or teaching? Already did my teaching. 4 months in Washington was enough. I'm a hardware store electrician. That's what I'm good at. The modern legacy. Frank's fundamental insight that emergency power doesn't need to be perfect or permanent. It just needs to work right now, became foundational to naval electrical doctrine. Modern emergency power systems include quick connect bypass cables, pre-positioned for rapid deployment. Temporary overload protocols, with calculated time limits. Emergency routing diagrams, showing bypass routes for when primary systems fail. The Naval Electrical Training Center at Great Lakes maintains a display. A burned electrical cable from the USS Pennsylvania, salvaged during her 1944 repairs. Next to it, Frank's original notebooks, donated by his family. The plaque reads, EM2 Frank J. Keller demonstrated that effective solutions don't require perfection. They require understanding the real problem and accepting calculated risks. Sometimes survival means choosing temporary success over eventual failure. Frank Keller died on September 12, 1987, age 67. His obituary in the Pittsburgh Post-Gazette identified him as Navy veteran, hardware store owner. No mention of ships saved. No mention of hundreds of lives. That's how he wanted it. But in the archives at the Naval War College, in training courses at electrical schools, in emergency power protocols on every warship in the world, Frank Keller's legacy persists. The moral of Frank Keller's story isn't about electrical engineering. It's about understanding when perfection is the enemy of good enough. The Navy's engineers designed perfect electrical systems. Redundant, safe, reliable, capable of sustaining power indefinitely under proper restoration procedures. Frank designed a system that was guaranteed to fail. Unsafe, unreliable, capable of sustaining power for maybe 20 minutes before burning itself out. The engineer's perfect system took 4 hours to implement. Frank's terrible system took 10 minutes. In combat, 10 minutes was infinitely more valuable than 4 hours. Sometimes the best solution isn't the safest solution or the most reliable solution. Sometimes the best solution is the one that works right now, even if it means accepting failure later. Sometimes temporary success beats eventual perfection. Frank Keller proved that innovation isn't always about building something better. Sometimes it's about accepting something worse, as long as it's worse in acceptable ways. His electrical bypasses were worse in every technical specification, but they were better in the only way that mattered. They worked fast enough to keep people alive. That's the courage to see solutions where experts see only unacceptable trade-offs. The courage to say, I know this will fail eventually, but eventual failure beats immediate death. The courage to choose calculated risk over guaranteed defeat. And sometimes that courage, applied in the most desperate circumstances by someone with a hardware store education and 3 notebooks full of hand-drawn diagrams, changes how the world thinks about problems. Electrician's mate second-class Frank J. Keller, 1920 to 1987. USS Pennsylvania, 1942 to 1945. 31 combat missions. Navy Commendation Medal. Developed emergency bypass protocol, taught fleet-wide, November 1944. His technique restored power to 23 ships, 1945. Average restoration time, 10 minutes, 40 seconds. Ships saved from loss, 11. Estimated lives saved, 840 plus. Still taught in modern naval electrical training. Still used in emergency power systems worldwide. I just didn't want the lights to go out when people needed them. Frank Keller, 1962.